Okay, now since we've introduced energy considerations, let's put them to use in a few problems. Take a look at this. A 0.5 kilogram bead slides on a curved track starting from rest at point A. The segment from A to B is frictionless, and the segment from B to C is rough. In other words, it has friction. So anytime you see the word rough, you mean it corresponds to friction. If you see the word smooth, it corresponds to frictionless. We take it to the extreme in terms of physics. Find the speed of the bead at point B. So we want to find the speed of the bead at point B. Say that 3 times really fast. We're going to apply conservation of energy between points A and B where there's no work done along the way. We have our one equation to rule them all. Kinetic energy at A plus potential energy at A plus any work done along the way equals the kinetic energy at B plus the potential energy at B. Your next question, once you write this down, is which, if any of these terms, might actually be 0. Well, we're going to start from rest at point A, so we have no velocity at point A, so our kinetic energy at point A is 0. We're going to go down to point B. We will be moving at point B, so we will have kinetic energy at point B, but we'll define that lower height at point B as being a 0 height, so we'll have no gravitational potential energy at point B. And for that matter, there will be no work done along the way because it's frictionless, so we have no work done along the way and no potential energy at point B. All of a sudden, the problem's gotten easier. We only have 2 terms left. The potential energy at A will equal the kinetic energy at point B. We can write that as mg, height at A, is equal to 1/2 mass times the velocity at B squared. I have the same mass on both sides, so I can divide through by that, get rid of that, multiply both sides by 2 and take the square root, and I have that the velocity at B is the square root of 2gh. How about that? It's that special case where you start from rest, you go down to a lower height with no friction, and your speed is the square root of 2gh independent of your mass. In this case, it's going to be the square root of 2 times 9.8 times 5 meters for our height, and that'll be 9.9 meters per second. So that is our speed at point B. If the bead comes to rest at point C, find the energy loss due to friction as it moves from B to C. So from B to C it's rough, and we're going to come to rest momentarily at point C, so we are going to lose energy along the way. How do we approach this? Well, we're going to use the same one equation to rule them all, and we're going to use it between B and C. So we have the kinetic energy at B plus potential energy at B plus any work done along the way equals the kinetic energy at C plus the potential energy at C. Next question, which of any of these terms might actually be 0? Well, we're going to define our lowest height in the problem as our 0 height, and hence our potential energy at B will be 0. We're going to have work done along the way. That's what we want to find, so that's not 0. And we do know we are moving at B, so we have kinetic energy at B. We're going to momentarily stop at point C, so our kinetic energy at C is going to be 0. And we can calculate the potential energy at C, but we want to solve this equation now for the work done along the way. So we got rid of 2 terms right away. We're going to subtract the kinetic energy from B from both sides, and we have the work along the way is equal to the potential energy at C, mg, height at C, minus the kinetic energy at B, 1/2 mass times velocity at B squared. We know all the terms, so we can put our numbers in. Our mass is 0.5 kilograms, G is 9.8, the height at C is 2 meters, and then in the second term we have 1/2 times the mass, and our velocity at B was 9.9 meters per second squared. If we figure out all these numbers, we get that our work done along the way is a negative 14.7 joules. The negative just means that we're taking energy away. Friction is working against sliding motion. It always is going to take energy away in that sort of sense, and that's what it did here. It was just friction doing the work. So it's the work done by friction is a negative 14.7 joules. Alright, let's try another problem. A mass of 0.8 kilograms is given an initial velocity of 1.2 meters per second to the right, collides with a light spring of force constant 50 newtons per meter. If the surface is frictionless, calculate the initial maximum compression of the spring after the collision. Alright, so if this mass is moving along a frictionless plane, then it's going to maintain the same speed right up until the point where it first hits the spring. So its initial velocity at the point where it contacts the spring is going to still be 1.2 meters per second. We're going to treat this as an energy problem, so we're going to look at that point at contact as being equal to point A, and then when it compresses the spring to the point where it just stops, that will be point B. So we have A and B. We have our one equation to rule them all. In the form here, I have energy at A plus work done along the way equals energy at B, which is indeed the one equation to rule them all. All of our kinetic energy plus potential energy at A plus any work done along the way will equal the kinetic energy plus potential energy at B. Which, if any of these terms, might be zero? Well, the spring is not yet compressed at point A, so our potential energy at A is going to be zero. We aren't going to have work done along the way because there's no external force. There's a spring force, but we've accounted for that by this thing called potential energy. So there's no external work done along the way in this particular case. And we're going to momentarily stop at point B, so our velocity at B will be zero and our kinetic energy at B will be zero. So this equation's gotten suddenly easier. The kinetic energy at A will equal the potential energy at B. Kinetic energy is A, 1/2 mass times velocity at A squared, is equal to the potential energy at B, which is totally in the compressed spring, 1/2 kx squared, because it's on the same level, gravitational level, so there's no gravitational potential energy. Multiply both sides by 2 and divide by k and take the square root to get the maximum compression. So x is going to equal the square root of mass divided by k times the velocity at A. That's going to be the square root of 0.8 kilograms divided by 50 newtons per meter, square root, times 1.2 meters per second. That comes out to 0.15 meters. So the maximum compression of the spring will be 0.15 meters. If the constant force of friction acts between the block and the surface with a mu of 0.5, and if the speed of the block just as it collides with the spring is still 1.2 meters per second, what then would be the maximum compression in the spring? So it's the same problem, only now there's going to be friction acting on it as it's compressing the spring. How do we deal with this problem? Well, we start again with the one equation to rule them all. Looking at point A and B, we have our one equation to rule them all, and again our second question will be which of any of these terms might actually be zero. We're going to have kinetic energy at A when we hit, but there's no potential energy at A again because we're on a level plane. We define that level as being our zero height, and the spring is not yet compressed. So the potential energy at A is going to be zero. But we are going to have work done along the way now. It's going to be negative amount of work done by friction working against the motion of the mass. So there is going to be work done along the way. We will come momentarily to a stop at point B, wherever that is. So the kinetic energy at B will be zero. Our potential energy at B will be the energy in the compressed spring, 1/2 kx squared. So there's our equation now. We just have one term. And we want to find, let's put in our terms. Our kinetic energy at A is 1/2 mass times velocity at A squared, which is just our velocity at that point. The work done along the way is the force times the distance, in this case x, which is actually a variable, but it's going to be the same x as we compress the spring, and cosine of 180 degrees, so that's going to give us a -1. So it's a negative force times x. And that's equal to the potential energy at B, 1/2 kx squared. All right. So we have an equation. We need to solve this for x. It's a quadratic equation. And we might as well just figure out what our constants are in front of all of our variables. So the force of friction is going to be mu times the normal force, mu times mg. So let's figure that out. 0.5, the mass was 0.8, and g is 9.8, so that's going to be 3.92 newtons. That's going to be F in front of the negative x. 1/2 mv squared is 1/2 the mass times the velocity a squared. That comes out to 0.576 joules. The 1/2 k is 0.5 times 50, or 25 newtons per meter. We're going to plug all that in to this equation, and that gives us one nice quadratic equation in x. Let's actually rewrite it. So we have 25x squared plus 3.92x minus 0.576 equals 0. Let's figure this out. Our coefficients, a is 25, b is 3.92, c is a negative 0.576. Put that into the quadratic formula, and we have x is equal to negative b plus or minus b squared minus 4ac square root over 2a. A negative b, 3.92, plus or minus b squared, 3.92 squared, minus 4 times a, 25. C is a negative 0.576, so we're going to have a negative negative in our radical here, which will be plus, over 2 times a, which would be 2 times 25. And if we add these together in the numerator, we're going to get 0.092 meters. We don't want to subtract, or we don't want the negative answer, because only the positive answer will make sense in this sense. The negative answer would be the spring going in the opposite direction, and it can't do that as it's compressing the spring. So we take the positive answer, 0.092 meters. So because we had friction, it didn't go quite as far. When we had no friction, it went to 0.15 meters, and when we have friction, it only went to 0.092 meters. Kind of neat. That's the kind of problems you can do with conservation of energy, starting from the one equation to rule them all. Just set it up, put in what you know, and solve for the unknown. Let's try another problem. See, these are all difficult situations dealt with rather easily using conservation of energy. A 50 kilogram block and a 100 kilogram block are connected by a string as shown. The pulley is frictionless and of negligible mass. The coefficient of kinetic friction between the 50 kilogram block and the incline is mu is equal to 0.25. Determine the change in the kinetic energy of the 50 kilogram block as it moves from A to B, a distance of 20 meters. Well, if we're dealing with energy, we have to deal with the whole system. So let's try that. Excuse me. So we have our one equation to rule them all. Now we're going to have mass 1 going up the incline, so it's going to go and it's going to actually increase in potential energy from a 0 value. Mass 2 is actually going to drop, and so it's going to decrease in potential energy to a 0 value. So we have to keep that in mind. We have work along the way, which is going to be due to friction. So if we want to find our change in kinetic energy, which would be our final kinetic energy minus our initial kinetic energy, we have to look at A and B, and point B will be our final position. So, rearranging this, we have that our final kinetic energy minus our initial kinetic energy, which is our change in kinetic energy, will equal our potential energy at A plus the work done along the way minus the potential energy at B. Sounds good. So change in kinetic energy will equal all those other terms. Now we need to figure out what those other terms are. To help us out, let's find how high we go from point A to point B from mass 1. We're looking at that triangle. Hypotenuse of that triangle is D, and H is equal to D sine angle theta, which is 37 degrees. So we're interested in H, which is D sine theta. We're also interested in the force of friction along the incline, which is equal to mu times the normal force. And the normal force in this case is m1g cosine theta. So friction is going to equal mu m1g cosine theta. So our change in kinetic energy is our change in potential energy for mass 2, m2gd. And we have our plus our work done along the way, which is going to be a negative force of friction times d along the incline, because the displacement is going up and the friction is going down 180 degrees between the two, minus the potential energy at point for mass number 1, which is going to be m1gh. Let's put in our values for h and our values for the frictional force, and we have this somewhat complicated equation, but we actually know what many of these numbers are, and now we can just put in our numbers. So the mass 2 is 100 kilograms, g is 9.8, d is 20 meters, minus mu, which is 0.25, mass 1 is 50 kilograms, g is 9.8, cosine theta 37 degrees, d is 20 meters as well, as it's going up the incline, minus m1, 50 kilograms, g 9.8, d is 20 meters, sine 37 degrees for our height h. All numbers, we calculate this out to be 11,745 joules. How about that? So that's the change in kinetic energy for this whole system, for mass 1 and mass 2, as they're starting from rest and going to some final speed. They both will have the same final speed because everything's connected. So we'll note that 1/2 the total mass times this final speed squared should equal our change in kinetic energy, because our original kinetic energy was 0. We can solve this for our final speed. Our final speed will be 2 times the change in kinetic energy divided by the total mass, square root. 2 times 11,745 joules over 150 kilograms, square root, 12.5 meters per second. That's the final speed of both masses. Mass 1 going up the incline, mass 2 falling. They both have the same final speed. Hence, the change in kinetic energy from rest for mass 1 is simply 1/2 mass times its final speed squared. So that's 1/2 times 50 kilograms, 12.5 meters per second squared, 3,915 joules. And the rest of that 11,745 joules is the change in kinetic energy for mass 2. All right. So many problems we can do with conservation of energy, and these are seemingly more and more difficult, but we can still approach these more difficult problems in a straightforward manner. The problems in the problem sets are actually easier than these. You always start with your one equation to rule them all and go from there, and look at the examples on edge creations if you need some help. But those should be really, really straightforward. These are kind of unique now. We're kind of getting into some much more difficult problems here, but still doable. A toy cannon uses a spring to project a 5.3 gram soft rubber ball. The spring is originally compressed by 5 centimeters and has a stiffness constant of 8 newtons per meter. That's our K constant. When it is fired, the ball moves 15 centimeters through the barrel of the cannon, and there's a constant frictional force of 0.032 newtons between the barrel and the ball. With what speed does the projectile leave the barrel of the cannon? All right, so we're going to have a force of friction for the whole time it's going through the barrel and for that distance. We still start with our one equation to rule them all. Kinetic energy at A plus potential energy at A plus work done along the way equals the kinetic energy at B plus the potential energy at B. Which of any of these terms might actually be 0? Well, we start from rest, so our kinetic energy at A is 0. We have a spring that's compressed, so we have potential energy at A, but it's decompressed at point B, so no more potential energy 1/2 kx squared at point B. We're all on a level plane, so no gravitational potential energy to worry about, so that is 0. And so we're left with a much simpler equation now. So we have our potential energy at A, 1/2 kx squared, plus our work done along the way, which is force times distance, cosine of 180 degrees. That's going to be a negative force times distance, is equal to 1/2 mass times the velocity of B squared. We want to find out what this velocity of B is, so we're going to solve for that. So, just algebraically manipulating that, we have our final velocity is equal to the square root of kx squared minus 2 times force times d over m. We know these values, so we can plug them in. K was 8, x is 5 centimeters, or 0.05 meters squared, minus 2 times the force, frictional force was 0.032 newtons, and it acted for the whole distance of the barrel, 0.15 meters. The mass was 5.3 grams, or 0.0053 kilograms. Everything's square root. Our final velocity when we leave the barrel, 1.40 meters per second. A lot going on here. Answered simply by setting up the one equation to rule them all and putting in all of our things that we know. How about that? At what point does the ball have maximum speed? This is kind of a more difficult twist to the problem. The maximum speed will occur sometime during the spring's release. Let's say at some spring compression S, because after the release the friction will continuously slow it down. So we want to find out where this S is. So the frictional force will now only act for this shorter distance, equal to the total distance x of the compression of the spring minus s, the point at where we've achieved this maximum speed. Start with the one equation, rule them all, put in our new modifications. We still have no kinetic energy at A, and now we have that our potential energy at A, 1/2 kx squared, plus our work done along the way, negative F times D, D being equal to X minus S in this case, is equal to our kinetic energy at B, 1/2 mv squared, plus our potential energy stored in the spring, which is 1/2 ks squared, because we still have that much still stored in the spring at that point. D, of course, is equal to X minus S, and X is equal to 0.05 meters, 5 centimeters. So we'll plug that in for our D. We now have 1/2 mass times the velocity of B squared is equal to 1/2 kx squared, which is a definite value, minus 1/2 ks squared, which is a variable value, plus F times S minus F times X. S is our variable. Solving for the velocity as a function of our variable S, we have velocity is equal to k 0.05 squared minus ks squared plus 2 times F times S minus F times X, which is 0.05 meters, divided by the mass square root. Alright, so we have our velocity in terms of a variable distance S. We wish to find out where the velocity is maximum as a function of S. So, in calculus, if you're looking for a maxima of a function, you take the first derivative of it and set it equal to 0 and solve for the condition that sets it equal to 0. So we're going to take the derivative of our velocity as a function of S and set that equal to 0 to find our maxima. Also could find our minima that way as well. Taking the derivative of what's inside as a function of S, we have decrement the power, so 0.5 times what's inside to the power to the minus 1, so we have a negative 0.5. And then by the chain rule, we have to take the derivative of what's inside the function. Well, whatever is constant is going to be 0. So we're really just looking at the S terms, and that's going to be a negative 2ks from this, and then the S term over here is going to give us a 2f left over, because the other one's constant and that derivative will be 0. So we end up with a negative 2ks plus 2f over m. And all this should equal 0. Now, this first term is going to be something, but this whole thing will be 0 when the second term is equal to 0. In other words, when whatever in the numerator here is equal to 0, that's when we hit our maximum value. That will occur only when negative 2ks plus 2 times the frictional force is equal to 0. In other words, Ks is equal to the frictional force. This thing will stop speeding and gaining speed, reaching its maximum speed at the point where frictional force is equal to the spring force. Makes sense. Can't go any faster then. That will occur at a point where S is equal to the frictional force divided by K, 0.032 newtons divided by 8 newtons per meter, and that will be at a point S equal to 0.004 meters. From the start point, that will be, since X was 5 centimeters in, that's going to be 5 centimeters minus 0.004, or 0.046 meters from the starting point. The actual maximum speed at this point would be the maximum speed that corresponds to the value of S, which we just found. So we're going to put that in, and we get 1.79 meters per second. All right, so that's about as hard a problem as we can imagine. Like I said, most of the problems in the problem set are going to be a lot easier than that as you set up your one equation to rule them all. Here's an additional thought at the end of this chapter. We've been talking about this conservation of energy, and we've dealt with conservation of energy, and in particular 2 conservative forces, that of gravity and that of a spring force, by using potential energy. So we didn't worry about work done by these conservative forces because we had already accounted for them using potential energy. Well, it turns out that if you knew your potential energy function for a conservative force, you can get the conservative force responsible for it by taking the negative derivative of that potential energy function with respect to the spatial variable. So in other words, if we had a conservative force responsible, the x component of that force would be a negative derivative of the potential energy with respect to x. The y component would be the negative potential energy with respect to y, and the z component would be the negative potential energy with respect to z. This would give us a vector force as a result of a scalar potential. More on this later in physics when we talk about something called the gradient. But here, we're just introducing the idea that we can actually derive our vector force from a scalar potential. And we would get an ijk vector force out of that. 2 examples are the spring force and the gravitational force. The spring force is 1/2 kx squared. What's the force responsible for that? Well, if I take the derivative of that potential energy as a function of x, negative, well, 1/2 kx squared, take the derivative of that, decrement the x squared, and you get kx, and then multiply it by negative. The force responsible for that is a negative kx, which is the Hooke's law spring force. Makes sense. What about the gravitational potential energy, mgy? We're using y as a variable in a vertical sense. So we have mgy. We want to find the force responsible for it. That's a negative change in potential energy with respect to y. Negative d dy mgy. The derivative of the y is just going to give us 1, and we have a negative mg. The force responsible for our gravitational potential energy is mg in the negative y direction. So it's the force of gravity, mg. How about that? We did this for 2 obvious conservative forces that we've been dealing with, but if we had other conservative forces and we had potential energy functions associated with them, we can find one from the other. Let's try a problem. Potential energy function for a system is given by u of x is equal to negative x cubed plus 2x squared plus 3x. Determine the force f of x as a function of x. Well, that's our potential energy function. We'll take the negative derivative of it as a function of x. Not too hard. For x cubed, we decrement the x cubed, and then we're going to have 3x squared for that. Negatives cancel out. And the second term is going to be 4x times a negative 1, or negative 4x. Last term is just going to give us a 3 for our derivative, and times a negative 1 will give us a negative 3. So there's our force responsible for this potential energy function. For what values of x is the force equal to 0? Well, we'll set this force function to 0 and find out. Use the quadratic formula, since we have a quadratic equation. Negative b, it's going to be a negative 4, plus or minus b squared, negative 4 squared, minus 4 times a, which is 3, times c, which is a negative 3. We're going to end up with a negative in our numerator here, which will be plus. So it'll be 16 plus something over 2 times a 6. We're going to end up with 4 plus or minus 7.21 over 6. Or two answers, negative 5.35 or 1.87, corresponding to a springiness going extension or compression. Either one, the force will be equal to 0 at those points. So that concludes the second video, just to give you some experience in using the one equation, the rule of Moll, and energy considerations for Chapter 8. Like I said, look at the edge creation examples. There's many of them, and it allows you to deal with many problems in mechanics just with this one approach of energy to the problem. It's a great tool.